All right, let's do some discussion of two-dimensional motion. So we've talked about one-dimensional motion. Hopefully things are starting to click a little bit. And so now with two-dimensional motion, it's basically going to be a very similar story, except that we've got, two dimensions to deal with. So for instance, if we talk about the position, here's a tractor. And we're looking at the position of the tractor. So we've talked about vectors. So our tractor now, its position will have two coordinates, whereas in one dimension, we just had one coordinate, right? And so here you can think about this position as being 5 meters, and in this case, at an angle of 40 degrees from the x-axis. You can also go through and figure out what its x and y components will be. And so this is going to make, basically our problem just a little bit trickier. We got a little bit more math to deal with in a case like this. And with a two-dimensional displacement, again, it works very similar to one-dimensional displacement, except now that we have two directions you can move in. And so the displacement, I'm going to call it delta p, is just our p final minus our p initial. We're going to have, again, average velocity, very similar equation. It's just that now it's p final minus p initial, where these can be two-dimensional vectors, right? And of course, we often will use x or y over here for this. And so in a sense, p is kind of my dummy variable, like the textbook is using s. And then average acceleration is going to be v final minus v initial. It's a very similar equation. It's just that now we've got the idea that there can be, that this velocity is a vector, and so it can be a two-dimensional vector. So it'll get a little bit, more complicated. And then we have the same sort of relationships for instantaneous acceleration and instantaneous velocity. And so let's look at an example here. So we have a flatbed railroad car is moving along a track at constant velocity. A passenger at the center of the car throws a ball straight up. Neglecting air resistance, where will the ball land? So pause this, think about this, and then we'll talk about it. Okay, hopefully you got at the center of the car. And so here's the big trick about two-dimensional motion, is that you can think about it as being two one-dimensional motions and always separate out those two motions. And so here we've got this railroad car. Maybe I'll draw it like this right here. Okay, that's moving down the line with some velocity. So in the x direction, we'll just do our sort of typical x and y. We've got this this cart moving with constant velocity, and then what happens is you throw this ball up. Okay, and so you're throwing it up, and just like a one-dimensional motion, it's going to go up and then come back down again. And so in your coordinate system, so here's you sitting right. Here's your head and your arms, and you throw the ball up. You're going to see the ball go up and then come right back down again to where you were. The ball has the velocity of the flatbed railroad car, right? And so in your frame, you see it go up and down. Now, if I was standing on the road, right, I would see the flatbed car sort of roll down the avenue there, and I would see the ball taking a path kind of like this here. And so I see two-dimensional motion, you see one-dimensional motion, but for the case where I'm looking at it, it's basically two different kinds of motion happening at the same time. There's, a ball going up and having the acceleration due to gravity, so our sort of free fall example in the y direction. And then there's the cart moving down the line in the x direction with a constant velocity. And so this motion, obviously is more complicated than the motion we've been talking about, but we'll always be able to break it down to two kinds of one-dimensional motion. And the nice thing is that when you do that, you can completely think about them separately, which makes life a lot easier. And so the trick that I like to say is that when we're doing these kind of problems, and so we'll focus a lot on constant acceleration in 2D style problems, you can treat each direction as if the other did not exist. And so we basically have two one-dimensional cases. And that was the example here, right? With that flatbed railroad car, that ball is moving constantly in the x direction, and it's doing free fall in the y direction. This will be a real common thing. And so hopefully we'll be able to see the patterns. And so the good news is that if you're kind of getting the 1D motion down, then it's really not too much of an extension to do two-dimensional motion. It's a little bit more math. You got to keep it separated, but you're going to see a lot of the same kind of things happening. And so all your experience in 1D motion is going to be able to help your experience in 2D motion. So same equations, but we treat each direction separately. So now, so here's the one sort of bad news, I guess, is that, when you're talking about these things here, is that it's going to be a little bit more complicated as far as the nomenclature. And so here, this is how I like to draw this. And so we've got basically, in most cases, we'll have, I'll break it down to a y direction and an x direction. And so these equations are the same equations we were just using. It's just now that we're a little bit more careful about what we're talking about. So we have two initial velocities. One is in the x, one is in the y, and we can possibly have two accelerations. And so a lot of these problems is going to be figuring out, okay, which, do I actually have two initial velocities? Do I actually have two accelerations? And once you do that, you build these equations up, right? And then you're going to use a lot of the same problem solving and such to move forward from there. So let's do a couple of examples. And so projectile motion is one thing that we'll do quite a bit of in 2 dimensions. It's sort of a natural fit. And so what happens is in projectile motion, this is a ball flying through the air. And so what we can do is we can kind of say a couple of things. First of all, we can say that the acceleration of the y and the acceleration of the x. And so like usual, I'll just do my typical kind of y-x thing here. And so in the x direction, we'll have an acceleration of 0. And in the y, it's going to be negative g. And so once you realize that, that series of 6 equations boils down to these 4 equations here. And so, like we said before, we're going to find that in projectile motion, you're going to have basically in the x direction, this is just the equation for moving with a constant speed. So there is no acceleration, so you're moving along with some constant speed of whatever your initial velocity in the x was. And then in the y direction, okay, you're going to be doing, in this case, free fall. So this is, basically these equations would work for that railroad bed car we were just talking about. All right, so let's go through and look at this. So here's a projectile example. And we're going to kind of go through and try to figure this out. So a cannon is fired horizontally off a cliff and it's sent out at 5 meters per second. If the cliff is 100 meters tall, how far from the cliff is the cannonball when it lands? So just like before, we're going to go through the same similar steps. So the first step, set up our coordinate system. So again, for me, I have my sort of typical XY coordinate system like this. You don't have to, but that's just what I'm almost always going to do. So then the second step is determine our constants. So in this case here, we've got some cliff. Maybe it looks like this here. And so in this case, I'm going to call the height of the cliff to be 0. This is going to be my origin, okay, which means is as the cannonball goes down, it's going to start moving in the negative y direction. So that's a little bit tricky. So in this case, the cannon is fired horizontally, so we're told this way, and so my velocity is this way. So my initial velocity is going to be all of that velocity. The initial velocity in the y will start out being 0. The cannon didn't shoot in the y direction at all, just only in the x. Now that'll change very quickly as time goes on, but the initial velocity is going to be 0 in the y direction. And like we said before, for ax it'll be 0, and for ay, so instead of saying negative g, I'll say negative 9.81. It's sort of the same thing. So again, first step, do your coordinate system. Second step, determine as many of the constants as you can. And the second step for me is I set up my equations. And so here's my equations then. And so because there's so many zeros, the equations are pretty simple. So again, like we were saying, you've got nice constant velocity in the x direction, and you've got some sort of free fall motion in the y direction. And so starting with these equations, you can kind of go through and hopefully figure out everything that you need to figure out. And so here's the physical picture. Okay, so at time 0, and this green line will be my velocity. My initial velocity is only in the x direction. So at time 0, that's what it looks like, and these are my velocity vectors. The next second, maybe there's a little bit of velocity going down. The x velocity won't change, right? Because there's no acceleration. So this velocity here and here will be the same. What we're doing is we're adding some. Now, the total velocity will be some vector sort of in between those, right? And that's increasing, but the key is the x velocity stays the same and the y velocity is going to start increasing. So if we go on, we'll sort of see this picture looks like this, and then eventually the cannonball will hit the ocean. And so one of the things that we typically would try to solve for here would be our final total velocity. Now the nice thing is we know already that my v0x isn't going to change. So we know the x component And so if we can find the y component, then we can find the whole total velocity. All right. And so what do we know about the cannonball when it lands, right? That's the trick here. We know its y direction position, right? So when it lands, it'll be at y is equal to negative 100. Again, the height of the cliff was 100, and I called the origin at where the cannonball was launched from. And so we can plug this into our equation and try to figure out when it lands. So why don't you guys stop now and see if you can do this here. So the question is, how long before the ball hits the bottom of the cliff? So take these equations we just solved for, and I really urge you to actually, try to do this. Try to stop and figure it out. Okay, so hopefully you got 4.51 seconds. And so how did we do that? Well, so here's my equation for the y direction. And so what I did is I set it up when it's equal to negative 100. What's nice is those two negatives will cancel. And when I went through and solved that, I got 4.51 seconds. All right. So now what I can do is I can plug this into the x position equation to get the final x position, which is what we were sort of looking for in this question. So here's my x equation. Again, I'm going into constant speed. So I plug in the 4.51 seconds and I get 22.57. So that's the distance that it travels in the x direction in this particular case. And then, if the problem asked, the final position vector of our cannonball is, negative 100 meters, and then an x distance of 22.57. So we can go from there and kind of figure out whatever else we need. Okay, so let's try one that's a little bit more complicated, but hopefully helpful. So here I've got my friend Chuck, who loves golf, so I'm using him here. So my friend Chuck hits a golf ball with velocity 45 meters per second at an angle of 40 degrees from the horizontal. What is the horizontal component of the velocity? So again, it's probably really important you pause here and try this one, and then we'll talk about it. Okay, hopefully you got for this one 34.5. So how does this work? Well, here's how I would do it. So again, I would make my x and y axis sort of the way I typically do. So y here and x here. And so the golf ball leaves with initial velocity 45 meters per second at an angle of 40. So here, one of the tricky parts is that you're going to have initial velocity in both x and in y. And so here for the x direction, right, so it's 45, an angle of 40. Now let me put this x in a better place. My x velocity will be 45 times cosine of 40. Again, that's the adjacent side, and so I get 34.5. So that is the right answer. However, it's useful to go through and find what the y velocity would be too, which is 45 times sine 40. So you need both of those. So you got to do a little bit of extra work here, to figure out what your some of your constants are to start out with. Right. So again, my first step, my coordinate system is the typical one that I usually have. And then my second step is to determine my constant. So again, I'll call where Chuck is hitting the golf ball at 0. And so now we have two initial velocities. And this is definitely a part that is tricky when you're first starting out with this. And so again, this is like I was saying before, this is one of those cases where, we're expected to use vectors as a tool, which is different than when you're sort of learning about vectors and you're going to use vectors. It's harder, I think, when you're just sort of expected. No one said there'll be vectors when I sort of talked about this problem, but you'll need to sort of figure to be able to use them. Okay, and then just like all projectile motion problems, again, my x acceleration is 0 and my y acceleration is negative 9.81 meters per second squared. So we can go over there, and my last step then is to figure out my equations. And so you'll notice the equations are a little bit more complicated than they were last time. So that's why we're doing another example, but hopefully you can sort of get this here. And so we actually have, again, initial velocities in both cases. And so these are the equations here. And it's, again, a very similar picture. It's just that it's a slightly different scenario. But again, we're moving at constant velocity in the x direction, and we're doing free fall in the y direction, which again will be real common for us to do that here. And so here's the picture of what the golf ball's motion would kind of look like. And so here I'm using the green arrow as our x velocity and the y arrow as our y velocity. And so what happens is as you move up, the y velocity is going to get smaller, right? So there's a negative acceleration right? So we know there's an acceleration of g downwards. It doesn't affect the x, but it does affect the y. So you can see here the y velocity will decrease as it goes through its motion. And at the top part, what happens, the top part is that the v0y equals 0. So this is real similar to within a 1D motion, right? So we could find out a lot about the situation by knowing that the velocity was 0 when it reached its maximum height. So this is similar, but it's got to be that the initial velocity in the y direction is 0, because the x doesn't change at all. The x is not affected. And so you can see that here in this picture. And then as it goes down, it'll come through and eventually land. Now what's nice is that there's a symmetry here. Okay, meaning that, if we neglect air resistance and truly the only thing acting is gravity, so the only acceleration we have is negative g, then basically this motion on one side will be exactly like the mirror image of the motion on the other side, every part of it. So if you find like the time, say for instance, to reach the max height, so time for a max height, then 2 times that time will be when the ball eventually lands. And so this will be the information that for a problem like this, you'll end up, finding it, this information will be really useful for you. Okay, and so again, the x velocity remains the same. The y velocity is always decreasing. It starts at whatever it was pointing up, and it's basically always decreasing, and then starts turning negative, after it reaches its maximum height. And the acceleration is always in the negative y direction. So I'll go ahead and ask you guys now. So we have these equations. So how long is the golf ball in the air? So again, go ahead and pause. It's really important if you're doing this, and haven't had a lot of experience with these, that you go ahead and try these before we go through it together. All right, so hopefully you got 5.88 seconds. So let me walk you through how I would do it. So again, the thing that we use here is something about the velocity. Like we just said, we want the y velocity to be 0. That's when it reaches the maximum height. And then the total time in the air should be twice this amount. And so we find the distance with our x position equation. So here's my y velocity equation, right? So we know that this is, again, this is the structure of this equation was that this was the v0y and then plus acceleration times time. And so what I want to do is find this for when v final is equal to 0. And so I go through and do this, and I get for my time 2.94. And again, from our picture, that time is right here. This is when the velocity in the y direction is 0. It's this halfway point. And so to get the total time in the air, we simply multiply by 2, and we get 5.88 seconds. And then so here we can take this equation, and so this is my equation for the x information, and so this tells me where this is, and so I get 34.5 times that 5.88, and this is also a very common thing that this problem would have asked you, is how far does Chuck's golf ball go? And so if we get here, we get this x here, and this thing is, again, such an important thing that we call it something special. We call this the range. So this is the distance that Chuck's golf ball went, and we'll refer to this as the range when we do this here. Okay, so that's an introduction, to two-dimensional motion and also constant acceleration in 2 dimensions. Here's the equations that we'll be using. And so, the best thing now would be to go and try some exercises. And so there's a PCQ tonight dealing with this one. All right, thanks so much. Hopefully this helped.